Hey, gonna teach you a little bit about how AI works. If you're ever curious, why does it do what it does? Um, I'm going to tell you a little bit about how it works from more of a computer science perspective, but also a real world perspective as well. So you'll kind of understand why it does some of the things that it does and maybe how to work with it a little bit better. So let's talk a bit about what we call essentially machine learning, which is sort of like the newest form of AI. And there's really three types of machine learning I'm going to talk about. The first is what we call supervised learning. So this is how computers learn and get smarter. The other is unsupervised learning, another way that they learn and get smarter. And then finally, reinforcement learning, where humans help the computer learn and get smarter. So we'll look at all three of those. But first, let's talk about what's called supervised learning. And so supervised learning is basically if you're trying to train an AI to distinguish between, let's say, dogs and cats, we just give it a lots of different kinds of data that's been labeled already. This is a dog, this is a cat, this is a dog, this is a cat. And after a while, when it sees enough examples of dogs and cats, it knows how to predict whether a new picture that it's looking at fits into one of those two categories. And we call it supervised learning because we're really supervising it by giving it labeled data, and then it tries to come up with its own conclusions. Now we don't teach it this is what a dog looks like because that's really hard, right? Like it's hard to, for instance, tell the difference between like a chihuahua and a blueberry muffin, right? Like if you had to write a set of rules to teach a computer how to tell the difference, what rules would you write? Like it's really hard, right? I mean, like you can't really do it based on the eyes or on the color, because a lot of these images are really, really similar. But humans can look at this right away, and somehow we just know, okay, that's a dog, that's a blueberry muffin, that's a dog, that's a blueberry muffin. This is a sloth, this is a chocolate croissant, right? So we would never make that mistake, but it's really hard to write a set of rules to teach the computer how to do that. And so we just give the computer lots and lots of examples. This is a cinnamon roll. This is a dog's tail. Like all of these things that look very similar to one another, we kind of train it in that way. And then that's called training data. So in supervised learning, you have to have a lot of data to train on. You probably on your phone, if you have an iPhone anyway, you've got an app called Photos. I know that Android phones have something similar. And it's already been trained. Before you got it, that phone was trained on popular kinds of images and different categories of images. So, for instance, these are pictures that I took at a baseball field. And when I search for baseball, it will pull up all of those pictures. Now, it's never seen those pictures before, right? Like no one taught it. This is a picture of something that has to do with baseball. But the training set, this phone, before I got it, was trained on lots and lots of example images of baseball fields and diamonds and things like that. And so it has learned through this supervised learning process how to associate pictures that have to do with baseball with the search term baseball. This is something else that you might have seen. And believe it or not, this is actually connected. So if we look at the upper left corner, that it's called a CAPTCHA. And it's supposed to tell the difference between a human and a robot. And the way they started was they would just say, type these letters in. Because originally, computers had a hard time reading letters that weren't perfectly typed. And so a human being can read this as V4X, BG, right? But a computer, in theory, would have a harder time differentiating. Well, guess what happened, right? The computers got a lot better at reading stuff like that. And so, in order to react to that, they made the captchas harder to read. And so, in the upper right hand corner, that's an example of a captcha where the human needs to read that in, and and then the computer needs to you know basically see if you got it correct. Well, the human being would type that in and probably V69, JVC, D, S, and then maybe that last V, is that a V or is it an L, or maybe it isn't anything because it's only supposed to be 8 characters, so maybe the first V is not really a V. So it starts to get kind of confusing for human beings to even read this. And then, guess what happened? Of course, technology being what it is, eventually the computers had something upwards of like a 94, 95% accuracy, whereas humans were still only 80% accurate. And so as a test to tell the difference between humans and computers, it was really no longer effective anymore because we couldn't say humans are always going to get this right and the robots are going to get it wrong sometimes. Now, in the lower left-hand corner, you'll see this morning overlooks. So what happened there is there was this guy, he was a professor at Carnegie Mellon, and he had this idea. The New York Times had a problem. You see, the New York Times had all of these articles and issues of the New York Times that were created before computers, so like prior to 1960, and they had it on microfiche, which is basically like a good quality photo of each page of the New York Times, but it was just a photo, it was just an image. And so you couldn't search the text of the New York Times until those were digitized, until they turned those photos of text into actual text. And so, the New York Times looked at what would this cost to hire enough professional typists to go through every article, every word in every article in the New York Times for the last, 60 or 70 years and type it into a computer. But there was a Carnegie Mellon professor who had this idea, and he said, okay, if we scan them in, let's scan in all of these images, and we'll isolate each word. And every time someone goes to Google or they go to someplace on the internet, we'll just pop up two random words and tell the human being, type in what word this is. And if enough people agree that that word says morning, then we'll say, okay, that's what that image says. And we'll associate that image with that word. And so in doing so, they managed to digitize all the issues of the New York Times for actually at probably nearly 100 years in less than 6 weeks. Like that's how quickly this went. And this guy was smart too. He took a commission of like a fraction of a penny for every time someone filled this out, and there were like 300,000 of these getting filled out every day. And after the course of that period, and this guy was like a millionaire, multimillionaire. So that's a smart, have an idea and then have everybody else do the work and then take a little bit of the money. Now, actually, a funny part of the story, guess what this guy ended up doing after he made his millions creating captchas for the New York Times? He went on and he founded another company that makes a product that a lot of you maybe use every day. And that product is Duolingo. So the guy who created Duolingo actually did these little CAPTCHA word things for Google. So that's sort of a little fun fact. All right, now the lower right-hand corner. I'm not a robot. Have you ever seen these? Yeah, a bunch of you, I'm sure, have seen these, right? Like, how does that work? Right? Like, if you go to this, why is it that we trust you when you say I'm not a robot, that you're not a robot? Like, somehow that passes the test. Why is that? You might have seen these, like a licensing agreement here. So like, you know, you check off the privacy policy and then you type in your name and your email address and then you type, I'm not a robot. Well, the secret to this is by the time you check that box, it has pretty much already decided whether you're a robot or not. And the reason is because it's tracking everything you do on the page. So the movement of the mouse, for example, when human beings move to check boxes, there's a slight erraticness about how they move the cursor. Whereas for a computer, like if you programmed a little bot or a script to go click that, it's going to go in an entirely linear fashion from one point to another. It's kind of like glide and scratch, like it's going to go exactly. And it's just not the way that humans work. And when you type in your email address, for example, the number of milliseconds between each letter is slightly different because it takes you a little bit of time, or at least for me, to look at the keyboard. I'm a hunt and peck typist, so to look for the right key. So it's that if you measure the number of milliseconds between each letter, it's going to be different. But if you tell the computer to type it in, it's going to go in perfectly. So that's usually by the time you click, I'm not a robot, like it will kind of know. Now, some of you who are thinking ahead, and some of you probably should be taking CS1 next year. Some of you are thinking, couldn't you program the computer to be a little bit random in between each of the keystrokes and, be a little bit random in how it moves the cursor? Yeah, absolutely. Absolutely. And so it's kind of created this arms race, right? Because if you can program it to do that, then you can also program a part of your program that tries to detect if someone has programmed it to be somewhat random. Because even for a computer, random is really hard. So even random for a computer is detectable. So there's a back and forth here of people who are trying to write robot detecting programs, and then people who are writing programs to get around the robot detecting programs to buy concert tickets and things like that. But I'll tell you, if they're not sure if you're a robot or not, what do? Well, they'll give you a little puzzle. They'll say, okay, figure this out. Pick which one's a flower. And so there will be lots of different kinds of puzzles and things to try to figure out that in theory are difficult at that time for computers to do. And then, of course, as computers get better, they make the puzzles harder. Some of you saw things like this when you signed up for GitHub, for example. And then you have these, right? Select all images with T. So you somehow have to look for things that you would associate with T and click those. All images with street numbers. And so these are all street numbers that are at different angles and at different lighting conditions and times of day. Here's one, all squares with street signs, which I always have a hard time with, right? Because like, what's the sign? Is it the sign part, or is it also like the legs of the sign? So like the lower right-hand corner, do you check that? Good question, right? I don't know. How about this one? Like all squares with traffic lights. Like, is it just the upper four, or do you also choose the pedestrian signal and then the pole, right? Like for me, like that is part of the traffic light, but again, it doesn't really matter, right? If 300,000 people say this word says the word morning, that's what we assume it says, even though the computer can't actually read that word. We go with the wisdom of the crowd. Same thing here. We're looking for what do most people say those squares are? Because the secret of it, folks, is that we are no longer trying to tell the difference between human beings and robots. By the time we're doing things like this, why do you think so many of these are traffic related, right? Like select all squares with traffic lights, select all the squares with crosswalks, all the squares with buses, right? Why is it that so many of these identification squares things have to do with traffic? Turn and talk to the person next to you and kind of, why do you think that is? Why did all of these have to do with roads? Okay, now some of you, some, yep. Now I heard people saying this. So it has to do with autonomous self-driving cars, right? Like we need to create cars that know the difference between a crosswalk and the regular part of the road. We need to find examples where cars can, for instance, like let's say you create a self-driving vehicle that can deliver your DoorDash, right? Like it needs to be able to read the street number in any lighting, any time of day. Obviously, we need it to be able to read traffic lights, right? From any angle, it needs to recognize it. These are things that human beings kind of know intuitively, but robots need to learn. And the way to teach them is through supervised learning, where we give them lots and lots of examples of labeled data saying this is a traffic light, this is a stop sign, this is a crosswalk. So every time you do one of these things, you're actually adding your vote to say this is this thing. And when they have enough data where enough people have said these photos are all of traffic lights, then they bundle it up and they sell it for tons of money to other companies. So when you do these, you are actually helping make money for the company that is collecting this data. You are essentially selling your data to that. And then there was I think a famous quote. I think it was might have been Tim Cook from Apple, but he basically said, if the service you're using on the internet is free, then you are the product. It's not the service you're using. You're the product that's paying for your use of it, because the data that's being collected from how you use it is monetizable. And so I think that's something good to keep in mind. Like for a lot of companies, the fact that we're using their service pays for it. But a lot of these great services that are free, including AI, right? Like money's got to come from somewhere. And if we're not paying up front for it, it's probably our patterns of behavior and our training data that's being sold. And I think it's important to know that. All right, so let's go on. So we talked about supervised learning. We're going to talk about the second type of machine learning called unsupervised learning. And so this unsupervised learning idea is basically if you think about like Spotify, right? Like, have you ever noticed that it'll say you'll like this other music, right? It's no one's teaching it. Like you haven't made a training set saying I like this music, I don't like this music. In essence, you've showed it enough things that you like, and it knows what other people like, and so it kind of looks for patterns. And so I can't tell you why I like the music that I do. I just like it. And I'm not sure that Spotify can tell me exactly why I like it, but it has seen enough patterns. Maybe it has a strong beat to it, or like a strong bass line or whatever. But it finds enough patterns in that to then recommend other music. And you know what? More often than not, I actually do like the music in my recommended playlists. So that's unsupervised learning. That's kind of working out really well. We also see this in medicine, and so they will show lots and lots of radiograms to AI, and AI will look for patterns. And there's evidence that shows it's able to find patterns that lead to earlier detections of cancer and tumors and things like that, even before human beings can pick up on it. And what's really fascinating about this in medicine is a lot of the time, like we don't know exactly why it has pulled out the set of radiograms that deserve a closer look, but and it can't tell us exactly why it pulled it out. It's just like something looks a little off. And then when we check it out, sure enough, we do more tests and we realize, oh, okay, this is a really early catch of this kind of cancer. So it's literally saving people's lives. This idea of using AI to kind of help detect formerly undetectable cancers in ways that no one can really explain how it's doing it. It's just it is cueing in on certain patterns through unsupervised learning. Now we've got the third type called reinforcement learning. And so for reinforcement learning, basically it's learning by trial and error. And so it tries something, we say, yes, that's right, or no, that's not. It learns, and then it goes back and it learns some more from that. So here's one example of reinforcement learning in action. And so this is a game you might have played before. You have a number of sticks. Like, let's imagine we've got like, I don't know, 8 matchsticks or something, or 8 pieces of paper, right? You can also play this with your fingers. Like you could have like, okay, like the total number of fingers in play. Like if this is yours hand and that's your partner's hand, there's total number of fingers in play is 9, right? And you take turns, so you can go, you can take anywhere from 1 to 3 sticks. You have to take at least one. So let's say I'm player A, I take 2. So there's 7 left. So then the next player says, okay, I'm going to take 3. So now there's 4 left. And then the player A says, okay, I'm going to take 1 stick. Well, player B at that point will take 2 sticks and stick player A with 1 stick left. And so player A loses. So that's kind of how you play the game. And if you have another person next to you, you could do like 4 and 4. I'll let you do this after my talk if you want. But this is kind of a fun game. And you don't have to use fingers. If you have like, coins or things like that, it works out. Now, you can do an analysis of this, right? And you can basically decide, okay, what do I take at every move? So let's say there are 4 sticks left. All right, if there's 4 sticks left and it's my turn, if I take 1, that leaves the other person with 3, they're going to take 2, I'm going to lose, right? If there are 4 sticks left and it's my turn and I take 2, that leaves the other player with 2 sticks, they're going to take 1 and I'm going to lose. So the winning move, if there are 4 sticks left and it's my turn, I have to take 3. If I take 3, that leaves the other person with 1, I win automatically. So you can do an analysis like this. And if you were a programmer, you could actually program it out and say, okay, if sticks left is 4 and it's your turn, then you take 3. Like you could program it in that way. But we can program in actually a reinforcement learning model to solve this. And it's actually fairly straightforward. So let me kind of present this mental image for you. So let's imagine I've got, let's say we're going to play out of 20, right? 20 sticks. I would have 20 buckets set up in a row, and I'd have a big number painted on each bucket. And that number indicates the number of sticks that are available at that point. And so I have a 20 bucket, a 19 bucket, an 18 bucket. Right now, in each bucket, I've got 3 ping pong balls, and I wrote on with a Sharpie marker on it. I wrote, okay, well, number 1, number 2, number 3. So I have 3 balls in each bucket. So here's an example. If there are 7 sticks left, I go to the 7 bucket and I pull out one of those 3 balls. And remember, there are 3 in there, right? So the chances of my pulling any given number is 1/3, right? 33%. Now, because this is computers, I'm technically going to take a copy. So there's still going to be 3 balls left in the bucket, but I'm going to take a copy of one of those and put that ball next to the bucket, representing the fact that, oh, I pulled a 3. So when there's 7 left, I pulled a 3. And so what I'm going to do is every time it's my turn, I go to the bucket with a number on it of how many sticks are left, and I reach in and I pull out one number at random and I put it next to the bucket. Okay. Now, in the end, if I win, all the balls that are sitting next to the buckets go back in the buckets again. If I lose, I just throw them all away. But if I win, remember it's a copy, right? So I pulled a copy of the 3 out. Oh, I happen to win, right? I picked 3 at 7, but then later on other things happened. But I ended up winning ultimately, so I put it back in. Now, if I go and I reach in, what are the chances that I'm going to pull a 3? It's gone up from a third. Now it's a half, right? Like it's a 50% chance I'm going to pick a 3 versus some other number. And so we keep playing like this over and over again. And if we play a bunch of times, each time we won, maybe we don't necessarily pick the same number and we ended up winning for other reasons or whatever. But every single time we win, we put that number back in the bucket, and it actually increases the chances that you're going to pick a number that tended to lead to a win at that point. And because these are computers, we can play this game many, 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 many times. And so you'll end up over time, you'll have many more of the balls that tended to win at that point. And that's essentially reinforcement learning. You end up with a computer that is a lot smarter at playing that particular game. And so, because it's a computer, you can just set it to run overnight. It's going to play the game millions of times. Now, it couldn't tell you necessarily why it's winning, but it gets really good at it. This is an example of a computer learning to play Super Mario, and it fails a whole bunch of times. But after a while, it tends to learn over time what works better. And when I say over time, because it's a computer, I mean, we're talking like, a few hours, whereas a human being might take, years to get that good, or lifetimes. This reinforcement learning model, this is how they created an AI that beat the strongest human chess player. It's also how they created an AI that made the strongest Go player that beat the strongest Go player. So the strongest Go player in the world now is not a human anymore. And Go has been around for thousands of years. And the computers basically learned how to beat the game of Go in, a matter of months. It's pretty amazing. This is actually a little video showing how reinforcement learning happened over. So after 100 training episodes, so it trained 100 times on playing Brickout, which is, and it's still not great, but again, it's learning over time how to get better, and you'll see it'll get better slowly. After 400 training episodes, what's really interesting is that after it trained it a whole bunch of times, what they found was that the computer kind of on its own discovered a strategy that is very effective in the game of Breakout, which is tunneling. So you tunnel through and then you hit the ball behind the wall, and it kind of bounces up there. So the computer kind of is going for that strategy on its own. No one taught it how to do this. The best human players learned that you could do this over time, or they taught each other. But the computer figured this out on its own, which is pretty amazing. So that's reinforcement learning in a nutshell. This is another awesome game. There's a lot of fun. It's called Quick Draw with Google, and basically you can sort of you try to draw with the computer, and the computer will prompt you and say, "Okay, draw a penguin in under 20 seconds." And then so as you try to draw it, it'll try to guess what it is that you're seeing, and it will try to guess overall. I think you have like 20 seconds. And if it can't guess what you're drawing, then you'll just go to another drawing. And when you do six of them, you'll end up with it'll show you kind of what it thought that you were drawing. But what I'd suggest is give it a try. You can pause the video and try it out, and just do a few of them, and then let's press play again, and then come back. So yeah, again, let me show you where it is. It's Quick Draw with Google.com. It's called Quick Draw, and give it a try. Play through a few times and see how good it is at guessing what it is that you're drawing. Okay, so we're back. And you'll notice that after you've drawn this, you'll see it'll show you what it thought you were drawing. And so, for instance, for a nose, it looks at examples of how other people drew noses. Now, you might have drawn a face for nose and then drawn like two eyes, a nose, and a mouth, and maybe circled the nose, and maybe it didn't get it. Because most people, when they're told to draw a nose, don't draw it that way. They draw it this way from the side. Now, does it mean that it's wrong that you drew it? Of course not. It really was a nose, right? But what we're going with is the wisdom of the crowd, right? Like, what do most people say a street sign is? Or what do most people say a nose looks like? Here's, what most people say cell phones look like. And so you look at over 100,000 images of cell phones, it kind of learns not just from the look of the cell phone itself, but also the order of the strokes that you go in. It kind of learns from that what the phone is supposed to look like. And eventually, right, it gets really good at recognizing what it is that you're drawing, just because it's seen enough examples of cell phones, right? Just like if it's seen enough examples of baseball photos, it's going to know from looking at a given baseball photo what that is. And so that AI technology that allows it to recognize stuff or discriminate between stuff, it can tell, okay, this is this thing, or this is not real. This is real. This is not real. Once we've trained that in the blue square, then we have this other piece of technology called a generator. And it starts with random noise, and it gradually removes more of the random noise to try to get closer to a picture of whatever it is that you've prompted it to recognize or to draw. So if I said, okay, here's a dog, I'm going to put in the random noise generator. It's going to try to randomly generate it, and then I'm going to say, okay, is this a dog or not? And the thing that recognizes dogs is going to say, well, either yes, that's a dog, or no, that's not a dog. And if it doesn't recognize it as a dog, then the generator goes back and tries again. And so it's this trial and error reinforcement learning where over and over again, the generator learns how to create stuff that's good enough to fool the discriminator. And once it starts reliably generating images from random noise that fool the discriminator, now you've created a generator that can generate images, for example, of real people. So for instance, this is called This Person Does Not Exist.com. And if you go to This Person Does Not Exist, every time you go there, you're going to get a picture of what is not a real person. So this actually is not a real person. None of these people are real. All of these are fake. They were all generated by AI using a generational adversarial network, which is this trial and error method of producing things. And then, of course, because this is the internet, we also have this cat does not exist. So, you know, to me, this is less impressive, right? Because cats all pretty much look the same, right? Like you've got a few different breeds, but people love cats on the internet. So lots of different kinds of examples of things. Um, so I guess, where are we going with this ultimately, right? Like you have this incredible technology that can generate stuff that looks real. How is it that we can actually use these things to do stuff that's actually useful, right? Like, I mean, generating cat pictures is pretty useful, of course, right? And no one's going to argue with that. But if we have this, this challenge overall of, suppose we challenged ourselves to say, you know what, let's use this AI technology to make the world a better place. How might we actually go about doing that? And I'll show you some examples of how we've actually been using it. I taught an app design class, and I had some students who created like a golfing app to kind of tell the you put in they were on the golf team at Menlo. And so, how do you create an app that allows you to select the right club, right? We also have challenged students to use the global goals. So globalgoals.org, this is where, a whole selection of um, countries got together to try to find what are the biggest problems that are facing the world today. So everything from poverty to fresh water, sustainability. And so I've had students create apps. They get together, they brainstorm, they create apps that have to do with, for instance, responsible consumption and production. I had a student who did a recycling app. This was solving the problem of not knowing what can be recycled, right? Like you go and you stand next to the bin, where does each thing go, right? Is this compostable? Is it recyclable? So this kind of helped with that. Um, we had students work on sustainability, and so here's a sustainability challenge that they did. This kid, like his dad, I think his dad worked with a landscaping company, and so he created this landscaping app. The kid did, working with his dad, where you could plan out green spaces and what would go in each green spot. I also give them this same challenge of teaching something that you know well. Hold on, just a sec. Sorry. So yeah, teach something that you know well. And this is what you're working on, right? You're creating a web app. So, this student, she did a prototype of an app that solved the problem of giving gifts to other people. You know how like birthdays and things like that, like you never know, how do I go about finding the right gift to give? And so she created this great app. Another student did one. What she knows really well are friendship bracelets. And so she created a website about how to create all the different patterns of friendship bracelets. Another student, she does Taekwondo. And so she did a whole website about the forms of Taekwondo that her school practices. And this is the one that did stuff with friendship bracelets. Um, and Maxwell did something having to do with shoes, how to choose the right like shoe, different kinds of shoes. So that was kind of cool. So again, like if you know it well, it makes it easier to create a website about it because you kind of know when you're using AI where the AI is steering you wrong, and where it isn't. Um, this girl did something on a personality test. So she did a personality quiz on paper, but then the website sort of analyzes your answers and comes up with insights about your personality. So, again, they used AI to help them with the app itself and then created something that other people could learn from, which is awesome, right? I think that makes the world better. We every May we have this great event called Share Fair. It takes place in the gym, and students, all the computer science students, create these apps about things that they love. Either games or things to teach people, like all kinds of things. And then we kind of people come around and they look at it and we talk about it. It's super fun. We had some students, they did a pull-up counter. And so they actually hooked it up to a camera. And so the camera tells when you're doing a complete pull-up. And every time you pull all the way up, like you hear a chime or something. And so it gives you credit for that. And it's a little bit more motivating to do the full pull-up. So yeah, all kinds of fun stuff. And then here's something that was actually very moving for us. We did this uh, so we had a member of the Menlo community, David Milgram, and he came to us one fall and he said, "Can you make an app?" My wife, Lucy, you see her on the right, she had developed a form of ALS, so also known as Lou Gehrig's disease, and so her vocal cords were paralyzed, so she couldn't speak anymore. And this was very sad because she had used her voice her entire life, and now she couldn't talk. And so he said, "Can you help me come up with a way to communicate with her using the iPad?" And so they worked with him to kind of prototype and develop this idea for an iPad. But just like you, they started with the whole empathy piece. Like, what is it like to not be able to use your voice? And so they actually came up with a prototype And these students promised not to use their voices at all for 24 hours. They actually didn't speak. They just tried to communicate using the tablet. And when they did that, they learned a lot. They learned about assumptions that they were making about what you would tend to write and how you would write it. And then they realized they had to build in the ability to sketch, kind of like the Google app that you saw, like to be able to sketch because it's quicker to sketch than to write words. There are all of these things that they discovered that they would not have discovered otherwise if they hadn't gone through the design thinking process and started with empathy and really understanding the problem before they build it. And so they worked on it for a few months, and in November, Lucy passed away, and it was devastating for everybody. And he came back to class to talk with us again, and he said, if I'm being honest, I kind of knew when I came in August to talk to you about this that it was probably too late for my wife. But the work you're doing has value. It's not too late to help other people. If you continue to work on it, if you continue to come up with this prototype, I can take this to other people and other people can benefit from it. And so the students redoubled their efforts. They worked to try to finish this. And I told them when we were working on it, I said, you guys have all taken CS1. So I know that you have a good foundation in computer science. If you want to use AI to do this, go ahead, because we're racing against time here. We have to get this done as quickly as possible. And so the students used AI or tried to use AI to help come up with this. And what was interesting, what they found was that AI was pretty good at doing certain things. But what would happen is they would say, can you write this networking component? And an AI would write it and would get it like 80% of the way there. And then they would have some tweaks and they'd say, okay, this one part doesn't work. Can you fix this? And AI would say, sure. And it would fix it, but then it would also rewrite everything else. And so often that would create other problems, right? So it never, when it's something complex, it never got it all correct in the first shot. And for them, because they had designed it themselves and they knew the problem really, really well, it was really hard to trust AI to kind of do it exactly the way that they had it in their mind. And so much of it, they ended up just writing themselves because they're like, you know what, it's quicker for me to I'll just write it myself. And that way it's perfect. And it's the way that I imagined it because they cared so much about what they were doing. And I think for things that you're doing with AI that you care deeply about, you're probably going to want to have more control over how it gets done. AI can be a great tool. It can speed things up, but you want to know what it's doing so that you can judge whether it's doing it correctly or not. And the only way to build those skills is to work sometimes without AI so that you can learn those skills initially. And that's why we have CS1 actually. So if you take CS1 next year, you'll learn those skills. And then when you go into some of the upper level classes, we'll say, yeah, absolutely, go and use AI because we know you know how to do this stuff. We can take on these really important challenges, these things that make the world better, these things that help other people. AI can help us do so much more of that because of its power, but you still need to be able to supervise it and teach it and reinforcement teach it in the sense of saying, yeah, this is right, this is not right. So AI really depends on you, the human, to be in the loop and to be in control in order to make good use of it. So I think that's probably the biggest thing to take away from this class is that you ultimately have to be the one in control. AI is like the genie, but you don't want the genie taking control. Like you always want to be in charge of the genie, right? So with that said, hopefully this is helpful. We'll talk more about how AI works, but we've talked a little bit about the three types of machine learning, supervised, unsupervised, and reinforcement learning. I've showed you lots of different examples. And then we've talked about some of the real world impact that AI has. And so hopefully this will help you when you start doing more of your prototyping to create a website about something that your client, your friend knows well. And so good luck with the rest of your prototypes and projects.